afternoon session, second day. And this session is mostly about on the topology optimization. So, and with the continuation with the yesterday's talk, my talk on design for AM, it is connected to the, which we have understood from the DFAM presentation. So, one of the biggest advantages of additive manufacturing is we can print the bionic designs, right? That is normally light-weighted structures. So weight reduction, which we need to in automobile industry, medical, right? And even automobile with specific to weight reduction or Formula One cars, right? So that is another area where, and even bikes also, if you see the race bikes, right? So wherever you have a light weighting or the weight reduction, and topology optimization is going to give, say, the best design, and then further you are going to fabricate through additive manufacturing, right? So in this session, briefly we'll give some aspects of weight reduction, and especially say with the medical application as well as the aerospace applications especially, right? So we'll demonstrate a software like N-topology, so how we can reduce the weight, right? So, and also lattice structures. We are going to cover two parts. One is topology optimization and other one is a lattice designing. So that is through N-topology software. And we are going to show you the one medical application, the bone, and other one is a lightweighting of aerospace and the automobile applications. So may I request Srikanth to take over.
Am I audible? Okay. Yeah, thank you, sir. Good afternoon, everyone. Myself, Srikanth. Today I am going to present a weight reduction methods. This will be very fun, and we'll see this. So, weight reduction, there are few methods are there. I think one method you know that we will see first. Three methods we are using. One method is the material substitution. Means what we are doing means traditional designs is there. Like suppose somehow how can we reduce the weight means using the lightweight materials, that is aluminum, titanium, these things we are using. Instead of steel we are going with the aluminum, titanium, so that we can reduce the weight because density is lesser for the aluminum, titanium compared to steel, right? So that is the one method, by substituting the material in place of steel we are substituting the material. The second method is the structural optimization. Like in the structural optimization also shape optimization, size and topology optimization is there, and mainly we are using the topology optimization. The third method is the lattice structures. Lattice structures means this is not a not a with new term, very like we might have often the term in the schooling days also. Lattice structure is the BCC, something like that, crystal structures. That only there only we get inspired. And the classification of the lattice structure is strut, TPMS, planar, that we will see in the coming slides. So this is like I told you, right? This is the past. I mean, in olden days we are right now still we are using material substitution, and presently we are using the structural optimization. And in future we will use the right now there is a research is going on, but industrial oriented point of view, like very few are using. So in future they will use this one once we get the standardization, these things. So these are the some of the lightweight materials and the applications and the showable AM process. As you can see, in lightweight materials, metals, polymers, composites and ceramics is there. And where we are using, I told you, right, instead of steel we are using titanium and aluminum, and that we can use it in the aluminum alloys, we can use it in aerospace and automotive application, and titanium we are using for the medical implants and all those things. And these are the some of the AM process that we can use it. Yeah. And this is the one, like in automobile, what is the material we are using, and this is the structure. You can see like so much of material is carbon laminate, means composite we are using on the outer body and all those things. And there is a confusion between the design engineers. Actually, there are two terminologies are there. One is like generative design and the other is a topology optimization. Both are like a apple and oranges, not like apple and apples. Okay, like two side of coins is there. On one side, generative design is there, and the other side, topology optimization is there. What is the difference between? I mean, first we will come to know what is the meaning of generative design. You might have heard this term, design and generative separately. Like if I say like I think everyone heard about the chat GPT, right? So there if you heard means you might have heard the generative AI. Same thing we are using. Means we are giving the some prompt is we are giving and it will generate the text, right? It will generate that answer. Same thing here also we are using the same thing. In Fusion 360 this we will use actually. There is only one software is there which are working on the generative design, that is Fusion 360. But topology optimization so many softwares are working. So in the generative design what we are doing means we are entering the some prompt and everything. Prompt means I am saying about the ChatGPT terminology because right now we didn't have the software. So, but topology optimization we will see. And so we are working on we are entering the prompt means we are giving the some constraints, objective, everything we are giving. So that according to that design it will generate the 3D model. That we call it as the AI models actually, artificial intelligence models. And the topology optimization means same thing. It will work on the AI model and this will work on the like some mathematical algorithm is there. There is one person is there, like his name is Bendos, who is working in the professor of the DTU, I think Denmark Technical University. There he is a professor. He is the one who found this topology optimization method. Like he is using the SIMP algorithm, solid isotropic material with panelization. He is a mathematician actually. So there you can use that algorithm. Based on that algorithm, that will remove the material actually. So we will see some of the examples with which is topology optimization, which is generative design, that we can see it. Okay. And some of the inspiration, like anything we are getting the inspiration from the nature only, right? Same thing. We are designing like previously tree means like complete solid is there, right? Some material we are in trees, but still the thing is it is serving the purpose, right? The main thing of the motto of the generative design means it should serve our purpose, whatever and it should enhance the performance also. Same thing here. It's like a tree, like instead of the solid it is there. Nature we are getting the inspiration, okay? And some of the applications we will see, like recent application this is there, and we can see the KTM juke bike, everyone might have seen this, right? This structure is actually topology optimized structure. Previously it might be like some frame is there, so that they have, because KTM bikes are very heavy weight is there. So they are using the topology optimization and they reduce the weight. And this is a recent example, like 1 month back they have implemented, like this is the Ferrari race car is there, and in that they have implemented the topology optimization bracket, so that they have printed also using DMLS, they have printed this Ferrari race bike bracket. And the third one is the Royal Enfield electric vehicle is there. This I think some 5 to 6 lakh is there Indian rupees. This cost is actually recently in Delhi Auto Expo they have introduced this one. They have showcased this model. There you can see this optimization is this body is there, right? And here also it is there. This is actually completely topology optimized, so that they can reduce the weight. But I told you, right, that should serve the purpose. So it is serving the purpose. And this one is the generative design, like a furniture we are using, right? This is not a topology optimization. Generative design is there. There we can see here. Bionic design has already told you, right? See, this is the bionic design. This can be manufactured using the additive manufacturing only. Bionic design means like some organic shapes is there, right? Or like our bone has a constant cross section, we doesn't feel anything. So it will change from geometry like one point to another point. That we can observe it here. So these type of structures can be manufactured by additive manufacturing only. That is the advantage of AM. And this is also generative design. Like the main purpose of the generative design is it should serve the purpose and increase the performance also. Later they will do, like this is like a architecture model, so they might have seen for the aesthetic appearances only. They did this thing actually. But for the brackets and all those things, that is not for the aesthetic purpose. It should serve the purpose like it should enhance the performance, like strength to weight ratio we call it as a. According to the weight, that strength should be maximized. We need to get the maximum strength to weight ratio. This is like some aesthetic purpose they did this thing actually. So the how generative design will work. Generative design and topology. And main thing, the main mode of the previous slide means both generative design and topology not the same actually. Both are different and the algorithms for both the things are different. That is the main thing. But both the things will work on the same type. The procedure is same, algorithm is different. How generative design will work means, as you can see in the slide, I look forward in time, I saw 14 lakh some times, right? Same thing generative design will work. Generative design will take the 3D model, original 3D model, and it should do the iterations. Iterations means it should do the some check it actually. Like how many steps are there so that your objective can be convergence actually, we call it as. And we might have heard this term like optimization. First I will tell you the topology optimization. Topology means geometry, optimization means getting the best results. So getting the best geometry we are calling as a. Like, so the meaning of the optimization is, we might have heard about this term like search engine optimization is there, SEO. Like getting the best search results. Google is good in that actually. Like out of the all search engines, Google will be the good. That's why people will prefer Google. And one more thing, like during the like optimization, right? Getting the best results by giving the some constraints are there actually there. Constraints and finding the best objective. Suppose we might have did the some Flipkart and Amazon shopping, right? There suppose I am searching for the best mobile, right? So best mobile I am searching, and what is the constraint, what is the objective is getting the best, like finding the mobile. Suppose if you find the mobile and you are getting a laptop result, means that is not your objective, right? So we need to find a mobile, that is your objective. And the constraint is cost, we will constrain it. And RAM should be 8 GB RAM, 16 GB RAM, 32 GB, like that we will say. Cost means some 20 to 30,000. These things these are the constraints. According to that, that will give you the best results, right? Same thing will work on the topology optimization also. There we are getting our main objective is to reduce the weight and increase the performance. And the constraint is like the stress should be, this should not be higher than your yield stress. Like we are applying a loading conditions, structural I am saying, we are applying a loading conditions. Suppose you are getting in your original design, you are getting some stress of, okay, still we are taking the example, and 625 megapascal as the yield stress, and in original design you are getting a stress of 300 megapascal. So the factor of safety is 2 almost for original design. So you are constraining that that should not exceed 500 megapascal so that we can get the maximum factor of safety, right? Or 600 megapascal, that should your optimization geometry. That should not exceed the 625 megapascal. That is what we are saying. That is our constraint. Like you can compare with the Flipkart product, how we are buying the product, right? Same thing. So that is it. And how many, like after getting the so many iterations are there, that we will see here. See here, you can see here. One person is sitting on the chair here, and this is the first, like these are, I told you, right? Some design, some features is there, some like here four designs they have given, but we can get the so many designs like that we will get it, like hundreds of designs we will get it. Instead of hundreds of designs, this is generative design actually, forgot to say. So instead of the hundreds of design, the software will automatically calculate which is giving the best result and which is giving the maximum performance. We are giving the constraints, right? Whether it is satisfied the constraint or not, that thing it will give actually. So the person is sitting on the solid body. This is the body, chair is there, right? In olden days, this type of designs are there. Later, how they are modifying means that should serve the purpose like sitting. So here we can sit it, right? That should serve the purpose of the aesthetic appearances. So out of all the designs, how many possibilities we are getting means only one possibility. It is not like this design is not good for aesthetic purpose, we can use it. But we can prefer these things. How many possibilities are there means only one possibility is there. That is the last one we are getting. Means that is the converged one actually. So, and then third one is the, like we already told you about the lightweight materials, right? So, material substitution and topology optimization. And the third one is the lattice structures. And what is the meaning, what is the use of the, okay, I forgot this. As already Sir told you yesterday, right? What is the importance of the weight reduction means in aerospace, if you reduce the 1 gram of weight also, even though that will increase the fuel, right? That's why, like while going the flight, they will ask you the checking the weight of the luggage and all those things. Why? Because because of that they can they can load the fuel account that, so that it should serve the purpose. So if we, that is a use of the weight reduction, aerospace, specifically aerospace and automotive, this will be very useful, and as well as biomedical also. That we will see, biomedical one bone we will see. So that is why we are replacing a solid body with porous structures. That we call it as a lattice structures or porous structures we call it as a. And lattice structures are this is the definition of the lattice structure. Like we might have heard about the term lattice structure, right? Definition of the lattice structure means array of the unit cell. Like in BCC, the very first time we heard about the lattice structure is the body centered cubic lattice, face centered cubic lattice, simple cubic. That was already there. Based on that only we get inspired remaining things. So this is the inspiration. I told you, right, body centered cubic lattice is there and honeycomb bees is there. Honeycomb bees, this is a hexagonal lattices, and this is like a butterfly wings is there, right? There, this structure we call it as a Warna structure. Means we can see here, this has some uniform pattern is there, but this is like there is no uniform pattern is there. That we call it as a Warna. And this is a bone, trabecular bone. If you cut the bone on the in between, this we can see it. Natural bone I am saying. We can see it, we can see this one. That we can call it as a TPMS. And the last one is the architecture. Architecture means you can see the like old palaces. You can see they might have installed this one like during the windows, and they will some grid type patterns is there, right? They will put the just for the ventilation. That we call it as actually porous is there, right? Why they are giving here also we can see this holes is there, right? That is like a pattern is there. That we call it as that hole is repeating in the all the direction. That we call it as a pattern actually. So that we can see it in the architecture and all those things. And the like Eiffel Tower is there. That is also we can see the lattice structure inspiration. And this is a geometry variation. This is a classification of the lattice structure, simple cubic, BCC. These all are like still here. Voronoi strut based lattice structures. I told you in the in between, right? Middle. Sorry. Yeah, and we can see this is a TPMS lattice structures. Most of the people will work on the TPMS lattice structures only. Why means the advantage of the TPMS means we can easily go for the printing and all those things. And strut there is some defective is there. The properties are good for TPMS actually with the same weight actually. So that is how gyroid and these are the 4 TPMS lattice structures are there actually. And the application, like whatever we are working, it should serve the purpose, right? These are the application in aerospace where we are using means like we already showed you, right? Topology optimization, like the brackets, panels, and all these things we can use it to reduce the fuel consumption. And in biomedical, medical implants and bones, these things we can use it, lattice structures. And defense means lightweight armor systems we can use it. And energy means heat exchangers we can use it. There is a that we can in the beginning slide we have seen that heat exchangers. Why we are using the lattice structures means to reduce the flowability. Like input we are pouring a permeability, that we call it permeability. In the input we are flowing a liquid. Suppose that should be like a halo is there, it will easily dump into the bottom, right? So if we put a porous structure kind of thing, so that will pass to the pores of the heat exchanger, so that the cooling temperature get reduced from the outlet. Input suppose we are sending through a like some 100 degrees Celsius is there. It may reduce in the outlet, we can get it like a 50 degrees Celsius because the passing time we are increasing, right? That is how we can use it in heat exchangers. And sports we have seen that we can see the applications also in the coming slide. And sports we have seen the footwear, helmets, and all these things we have seen. And the consumer products means like textures and all those things, there they can use the consumer products. And this is the application, one app we have designed, like we can see the app here. Yeah, this is the application of the lattice structures. It may go fast. Like fashion we can see, and home appliances where we can use the lattice structure. Okay. And yeah, we need to acknowledge the NTOP. This is the project we did, like lattice structure application. We can see here branches and all those things. The text may below. Like we need to thank to the NTOP actually first of all. Like they, because they have given the student lesson to explore the software, and we did this project actually. And this is my bio. Okay. So with this, so with this brief introduction about the lattice structure and all those things, we can go for the. So any doubts on that? Like any application you want to know, like. So with this brief introduction about the lattice structure, we will go for the NTOP software. There, what we first I will tell you the brief introduction about the NTOP. What is the use of the NTOP, and what is the difference between the other software and this one. And NTOP specifically mainly designed for the lightweight structure, and how we can manufacture the lightweight structure. I will show you the design so that you will come to know what is the significance of the additive manufacturing. And people might have worked on the subtractive manufacturing and all those things, so that they will come to know whether the structure is possible to design or not also. Okay. So the main purpose of the NTOP means specifically used for the additive manufacturing purpose only. Like we can design the lightweight structures, like I told you the designs and all those things, right? Application and all those things. That was designed using the NTOP only. Okay. So we will go for the like we have some. I will tell you how to generate the lattice structure and how to use it for that. Like if you want to know any further, please let me know now so that I can proceed further. Okay. Or any doubts till now? Like I will design a one simple cube. I will take it and I will tell you how to generate the lattice structure and what are the types of lattices are there. And one application also I will take it, and tensile coupon I will take it, how to generate the lattice, and two applications I will take it. Time permits, I will go with the second application, that is automotive application, and the first application is the bone. We will take it. Okay. So what NTOP will do, I will tell you. Like some traditional softwares are there, like SolidWorks and Creo is there. You might have know about these things, right? There, what we are doing means first we will design in SolidWorks. We will design the 3D model using the 2D sketches, right? Suppose if I ask you to draw a cube, like this water bottle is there, right? That we cannot draw it in the NTOP actually. We cannot design it in the NTOP. That we can use it in the SolidWorks sketches is there. First we need a sketch. Sketching we cannot do, but the 3D models we can play with the 3D models in NTOP. Okay? I mean formerly known as the NTOP only. Now they call it as NTOP. Okay? Don't get confused. Yeah, like you will get the STL actually here in NTOP. STL. Why STL I will tell you. Because yeah, you can see. Okay. Why STL I will tell you that. That I will take care of. No. Actually this is the licensed version is there, but you will get the student version for 14 days. Yeah. No, you can import the 3D model. Like I will show you. I will show you what are the formats it will support. Okay. Like, but if I want to say, I can say like step file it will support, and STL it will support. Database obviously it will support. Okay. That we can import. Yeah. Because I have designed in SolidWorks only. That format only I will import it, and I will show you. Okay. That we don't actually, because I am not the supplier. No, I am using student version only. No, this we got the license from them only. So right now it is going on. For this only we took it actually. Student version is there. There is a student version for 14 days. It is there actually. Yeah, just to explore actually. That you need to request them actually. In NTOP website there is like get a student version for 14 days. It is there actually. Yeah, thing is this is actually cloud based one. Like you need to connect with the internet. Like suppose for suppose if you are not using the for some 10 days or something, it will ask you to log in again, because they will take the data what you whether you are using the for the right purpose. So yeah, where we are, yeah. Is that okay? So is the dark mode okay? For you it is okay, right? Otherwise I can change the mode to light mode. Fine, right? Okay. Yeah, here, yeah. Yeah, what we are doing in the conventional design software means we will take a 2D sketch. Suppose I told you, right, if you want to draw a water bottle or something, in Ento we cannot do, but in SolidWorks we can do, and we can extend that model. Extend that model means we can take that 3D model and we can use it in, to reduce the weight and to add the texture and all those things. Texture means something like some different patterns is there, right? Customization. That we can do it in Ento. So 3D models means basic 3D model we can do, like cube, cylinder, these things we can do, cone shape, these things we can do, but we cannot do a 2D sketches and all those things. That we can do it in the SolidWorks. So we need to know the other CAD software, SolidWorks, KTR, Fusion 360 or Creo, anything. Then we can import the 3D model in here. Okay, that I will show you. First I will tell you I will explore the simple cube. I will take it not from here only. I told you, right, simple cubic designs we can do. Okay, so this is the lattices, we can go with it, and you can see them some text will automatically appear, so that you will come to know, and you can, if you want to know, you can take the help. I will tell you how to take. See, here it is there, right? You can take like that. Like what is the meaning of that? I mean, like provide the input and box, these things we need to input. Volume means, and one more thing, the good thing about the N-top I will tell you, like for my personal experience I will say, like we have designed actually some GCC, FCC lattice structure in SolidWorks long back before the N-top. The problem with the FCC designing the FCC structure means, lattice means repetition of the unit cell. Like you have seen the Rubik's cube, right? Rubik's cube 3 by 3 by 3 by 3 is there, right? Or some 6 by 6 by something is there, right? Some pattern is there, that unit cell is there, that will repeat in the 3 directions. So once we design that unit cell, then we can repeat in the all directions. But in SolidWorks there is a problem with that means, once we go for the repetition of all those things, it will extend the memory, and so that your system will get hang. That we already faced it actually by designing the unit cell now also. But here it will take very like milliseconds. It will give you the, it will generate the design, like when we have seen the lattice structure and all those. How it will generate the design means, nowadays this is also maybe SolidWorks may use, they are using the implicit modeling actually. Implicit modeling can give you the faster results actually. So that we will see. And means implicit modeling means implicit bodies they are using. Okay, so rectangular volume lattice we took. If you want to go here, or you can search it here. Add block is there, right? This we can use it as a search engine. I usually prefer this one, so that I can search it whatever I want. Okay, so lattice I put. So volume means, I told you, like 3D model. Since we didn't import anything, so I can take it from the N-top only. That volume I can take it as a cube model or cylinder or anything. I will take it as a cube. Okay, so I will search it here, cube. See, we are getting a cube, right? So I will take the cube size as a 30 mm by 30 mm by 30 mm, or 50 mm by 50 mm by 50 mm. Okay, okay. And the unit cell means, I told you, right, there are three types of unit cells are there. One is like a 2D lattices is there, and the other is like a PVML means literally periodic minimal surfaces, and there is some mathematical things are there. I don't want to go for that. Yeah, like when I call it as a minimal surfaces is there, PVML is there. That is a pattern show you. See, if you don't know, like if you are a beginner in the NTOP, like since I'm like, I know the software, right? So I know what input I should give. So if you are beginner in the NTOP, what to do means you just press on the double click on it. Empty is there, right? We need whichever the optional is there, that you no need to keep, because that is optional. Empty means you should keep so that to get the design. Just press on the double tap on it, double click, so that it will give you the available options. These are the options you can use. So I will use the graph initial. I will use the option initial. First I will use the graph initial, and I will show you. Okay. So again empty is there, and this is the ribbon is there, so that we can see the available options. See, these are the types of lattices are there. It's strut based actually. Okay. And hexagon and honeycomb is there, that is 2D, they have combined merged with the graph. So these are the types of lattices. BCC I told you that first we will see the BCC, how it will generate the BCC. And something like unit cell size I have given. So 1000 unit cells are there in that T01 Lattice. So by combining all the unit cells, we call it as a lattice. So I will show you the how BCC will structure will look. See, you can see this is a graph view, means line diagram. I told you, right? And if you want to go implicitly, you can see. See, this is how BCC will look. I will reduce the thickness. Okay. And if you want to show the FC simple cubic means this is how it will look. Okay. And the FCC. This is FCC, right? Face center. All faces are centered. And diamond. Okay. And there is some controls are there. Controls I am not saying, because these controls we can customize it. Like suppose if you are using the SolidWorks or something, according to that you can customize it. I will show you that. Yeah, camera control setting. Suppose if I am in SolidWorks, NX Creo is there. Whichever software you are familiar, you can customize the control settings. Since I am familiar with SolidWorks, I will use this, so that the remaining zoom in, zoom out, everything will be same. Okay. So this is the diamond, and one 2D lattice we will see. Hexagon and honeycomb. I showed you in the inspiration of the honeycomb bee, right? Implicit view. See, previously we have seen that the direction is changing, but it is like a 2D is there, like some pattern is there, we are extruding. There is no 3D. 3D means simply extruding the 2D pattern. But in lattice, in BCC, this is not like this, right? That is the difference why we are calling this as a 2D lattice. And 3D lattice means PPMS, strut base, all these things are 3D lattice. So that's why we are calling this as a 2D lattice. So we can go with it. And one good thing about this is re-entering. This actually, anyone heard about this term re-entry? There's some specific properties there actually. Direction, if you try, you will get the negative Poisson's ratio. Okay, this only we can extrude, then we will see this. So thickness I will keep it as a this is MPC, not optional. So we need to keep it. So thickness I will keep this as a 1 mm so that we can see. See, this is loading. See. So if you want to see the clear view means, can see the rendering quality also you can see, but always prefer low quality. It depends on your graphic card and all those things also. So if you prefer the low quality. By 800 you can take the 8 GB. It will take time. Yeah, no, no. Like the cube which I took the from the NTOP only, right? That these simple designs are available in the NTOP. Suppose if you want some tensile component, we cannot draw in NTOP. We need to took the advantage of the 3D CAD software like Creo, Fusion 360, NXV, whichever you are familiar, that we can take. We can take, and you can. The universal file format means step file. Like the some softwares, like every software can accept the step file actually. Like why we are using the step file, why we are calling as a universal file format, any idea? That we call it as a universal file. STL also, for step file we call it as a universal file format. That, yeah, 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 yeah. Yeah, I will tell you the example. Like suppose you have designed one model in the SolidWorks file format, and you might have sent to the customer in the, you might have sent the 3D model to your customer. Like I mean, as an industrial person, I'm saying, you need to send to your, show the 3D model to your customer. Like if you send it in STL PRT file, and the problem with that, he should have the SolidWorks format. Suppose he might have the Creo also there. He is having a like 3D model software is there, or some other online resource is there. In step files can open in online resources, some online resources are there. The STL will open. STL viewer is there. In online resource also we can see. We know it. nowadays we are getting a 3D viewer also in Microsoft. So tensile ending, see here you can see here is I think one person asked the available file formats, right? This is the available file formats, it can accept it. You can see STL is there and OBJ is there. What is it? As already Sir told you yesterday, OBJ means like the texture we can see wavefront object. Okay. Yes, step is there, inventor and SolidWorks, Annex, Creo, everything is there, right? These are the file formats NTOP can accept, and in future this may add actually. So our file format is already there, so I will keep the all compatible files. So SLDPRT is there and step file is there. So we can take that as we can take the step file or SLDPRT. Both are same only. I mean here. Okay, I will take this step. Okay. See, my intention is to, as I already told you, right, lattice structures. If you are doing previously, we have designed the how we can say, like, you might have heard that design space and non-design space means. What is the meaning of design space? I will tell you. Design space means your intention where you want to modify the design. That we call it as a design. And where your design won't change, that should be keep it as a original. That we call it as a non-design. Here what we are doing means this is the tensile specimen, right? Here in between, in the middle only. Suppose if I am designing my model with the 3D SolidWorks means, I can. This is actually three models actually. See, you can see. seen here, three bodies is there. So left, middle, right. Okay. These three bodies I have divided. Why I have divided? Means my intention is to keep it on the middle body only. So I have divided. Now you can suppose you have the extension. Bone is also there. Right? Bone also in between also I need to put the lattice. That we can see how to do this also. First we will take this. Similar example also bone also. First we will see this one. What sir? It is like in abacus also we can do, or in entop also we can do. Structure like suppose we are keeping this one actually, and in between we are applying the lattice, right? So one end is fixed and the other end we are applying a load actually. So no, we can combine it. We can combine it. I told you right. Like suppose before doing the simulation also we are going for the printing, right? If the parts are separated, we cannot get the correct print. So we are combining the three bodies actually. So for that we are using the Boolean union operation. And so it is with Boolean union subtraction technique. I will show you. Yeah, it is there. Like you need to define that. This is the space and this is not the space. In SolidWorks I have defined this one. Because this option we cannot do. This similar example is there for bone also, where we can define how to do this. Okay. Yeah, but this is from that we need to take the we need to take the decision. If you want to take the throughout the body, then you don't need to define the design and not design. That's the example I will tell you. Where what is the meaning of design and non design? Yeah, brackets is there, right? Yeah, you might have heard it. I will tell you the example. That one I will discuss. So suppose what is the meaning of design and non design? First I will say. Like sir has already told some brackets is there, right? Brackets and holes are there. Holes and everything. Why means one hole can be fixed and another can be fixed. Fixed means bolted joint we are applying, right? That is fixed we call it fixed. Suppose if you are applying the hole on it on the lattice body, we cannot keep the threads and all those things, right? So that we call it as a design space. Whatever the holes and bolted joints is there, that we call it as a non-design space. Means our lattice should not touch this. That we call it as a non-design space. Using these terminologies, then we need to see the topos of the building. As well as the lattice also we can see. We can adapt the space. I can adapt the space too. In lattice space also we can use the lattice. Topos transformation, all we can remove the design space. We can see this. Then remove the median if you didn't define the design and non-design space. Design non-design space means that will remove the median in the specific design space only. Then this will avoid the non-design space holes, bolted joint those things. Same thing also lattice also is there. One example is there plate color. I will show you. Where you will get to know. So this is the lattice body, and see, I already convert into implicit body. How to do this means just press on the double press it, convert into cat body to implicit body. Okay. So these three bodies are there. I already rename it as a left, right, and middle. Okay. Now I won't combine because my aim is not completed. Aim is completed means I need to apply the lattice immediately. After completing my objective, then only I can combine the three bodies. So left is this one. This I can't apply the lattice body, right? I don't want to apply the lattice body. And then this is right. Here also I don't want to apply the lattice, okay? This is middle. My intention is to keep it here only. So what I took means here I took C. See, I apply a lattice here. Now we can see like this it will come actually. hole is there, right? I will keep this here. See, this is called, we call it as a pores. So we have, I told you, right, some fluid application we are using the, like if you pour a fluid or something, it will come out of the liquid through this pores only. Mainly the thing is permeability also we can calculate using this lattices also. This distance between pores we call it as a 2 mmc. Actually each unit cell, you can see it here. Yeah, yeah. Yeah, mainly specifically TPM of lattice is suppose that is suppose if you ask specifically the gyroid is a one stick. Here we are using the gyroid only. I will show you the gyroid. It depends on the, yeah, it depends on the curvature also. I will show you here. Yeah, mean surface is like TPMS means the zero mean surface is there. So simply periodic minimum surface is there. That structure itself we call it as a TPMS means that is as a zero curvature is there. So the support can be less than 45 degrees so that we can filter without the support. We have tested also these things also. Yeah, we have 3D printed using as well as so this is a structure, our middle part is getting like this, and you can see left body, right body, but now this is not even combined, right? So I applied a Boolean union. You can see here Boolean union. See, I told you, right, and top, like after completing our retention we need to combine the three bodies. Here I combined, here you can see this is lattice body and the left body, right body, you can see here. Okay, so that we will get like this. See, now the dash line is, previously we have seen the dash line, right? See, now once I combine this, that is gone, right? So we have combined the bodies. So we can mesh the 3D body and like why SCL means this is like a intricate geometries are there, right? See, if I want to capture this sharp curvature of geometry, I need to use the tessellations only. Like some solid body, some triangle, like some solid object, original body that we can capture in the IGSR step format. But to get capture the intricate, like very precise geometries means we are using the tessellations only. Okay? Why tessellation? Why triangle in area? Like why triangle? Why not square or something? Why can't we capture with the square? Why triangle? Why STL is called it as a tessellation? Yeah. To get a closed surface, triangle is the minimum number of lines we are getting. Suppose suppose I have given the two lines, right? You can draw like this, but there is one gap is there. You can close it like this. So to minimum number of lines to close a surface means 3. To draw a square means I can draw one more line. I can say the triangle. And if you draw one more line, it will become a triangle only. Whatever the number of lines you can draw, that will increase the accuracy. Triangle. That's why we call it. We are using a translation triangle. And in 3D models also for complex structures also, during the analysis, like in industries, they will prefer the tetrahedron instead of the hexagon to get the correct capture. But the problem with the tetrahedron is it will increase the element sizes. That's why STL file size will be very high. Tessellations will get increased. So they will use the tessellations. If it is increasing the element size means obviously simulation time also will get increased. once we combine this one, this is how we are getting a 3D model, and you can export into, you can mesh the 3D body. I will show, but I can't mesh from implicit body. This is once we, yeah, this is the one I told you, the implicit body, right? Whatever the, like universal, whatever the bodies that are generated in the endo, that we call it as the implicit body. Here also there is no cat body also. Cat body means you can touch the faces here. Here you can see this is the, I will show you. See, I can touch the faces, right? I can touch the lines, right? I can touch the points, right? And this is implicit body. Suppose I want to convert this into cat body, I can convert into cat body, create cat body variable. But the problem with here means I can't able to touch it, because that can be converted into the implicit body, that can be taken as a one body only. So once we combine the Boolean union, then we can mesh the implicit body. And the how to, like suppose if you are a beginner in the NTOP means how to learn this means, once our aim is completed, then we need to convert into STL body, and I told you right, implicit body, you can just search it here. We need to do mesh, right? Available options will come, whether is it a cat body, no it is not a cat body, right? Implicit body. So implicit body DC is there. One more thing, this is recently they have added DC. Why they have added means just to, I mean, people they have complained actually, like I will say one thing, I can't mesh, but I will say one thing. See, we are using a meshed body, right? The thing is, I told you STL we are using for the like detailed, intricate detailing STL triangles. Very less size triangles we are using for the intricate geometry. But see here, this is not an intricate geometry. This is completely solid, right? We don't need that much of precise tessellations, right? So if you are going with the mesh from implicit body, it will take it everything as the same type of tessellation size. But if you go with the mesh from DC, it will automatically calculate. Like this software, like this is a original body, so here we can capture with the 2 lines of diagram, this one, and here it will increase the tessellation, so that your file size get reduced if tessellations get reduced. So we can prefer the mesh from DC or mesh from implicit body DC also. So this one. So once we completed this one, and yeah, why I am saying means how to identify the, there is a shortcut. You can see the icons here. What does it mean? Means there are 2 types of understand. I mean, NTOP is all about Boolean union and understanding also. Like you cannot get that tutorial software, but there is this type of software. So once you understand, you can play with that. So you can see the implicit body is there. I am touching here, right? Means it is asking that it is put it in the implicit body, not cat body like that. Or otherwise, there is one more term is there. I told you, right? Double click on it. It will show you the available options. For me, I need to keep this body, implicit body 5. So I will click on it. 5 is there, so I can put it. Or otherwise, one more method is that every time it won't work. One more method is the logo icons. You can see. You can see here, right? Icon. The same type of icon where it is there, that type of bodies it will accept actually. See here also this icon is there, right? So this will accept, and here also this icon is there. This will accept like that. See, right? Right, like that. And the tolerance and all those things, the mesh size and all those things. Okay? Like if you have a good system, you can use the, you can run the invoice system and invoice system. Now we need the 3D print this, right? So we need to get the 3D models STL file for it. But if you keep the very low tolerance with our STL file size will get increased. And the build time will while importing the build software also, processing time will get increased. But if you are thinking about the precise geometry means go with the less 0.2 mm or something. And it depends on the this size also. Suppose the thickness is a 2 mm means we can go with the 0.3 mm. The thickness, the wall thickness is there, right? Suppose that is a 0.5 mm something or means we can go with the 0.1 mm precisely. So So we cannot capture the 0.5 mm thickness with the 0.5 mm tolerance, right? So that is why. So that is how one thing we can do. Tensile we can do. Any doubt till here? You understand, right? So first what we are doing is we have imported the 3D model. We have already designed in SolidWorks. If you want to show, I will show. This is the 3D model we took, and we have drawn the lines here. Separate I have extruded. See, first I have extruded this one. Three bodies I have extruded, and I didn't combine actually. See, there is option called merge result, right? If I merge result, what will happen? We'll see. See, two bodies. Three can change to two. Merge result. See, 3 can change it to 1. 2 can change it to 1. Okay? Or otherwise, combine this one. Again, only one body we are getting. Suppose if you are getting this body, you can do still you can do in the end top also. That example we can see it for the bones. Why? Because why can't we do it in the SolidWorks? Means bone is a STL file geometry, because that is a 3D scanned geometry, right? So we cannot design the bone patient to patient. We can scan the 3D model and we can get it in the STL file tessellation format. So bone is a STL file format. So we can play in end-top bone, end-top available option. How to cut the geometry, how to define the design space, non-design space. Okay. Yeah, we can do so. Yeah. In bone we are using gradient only because we need to vary the properties like the Young's modulus is there, right? Yeah, we can define. We already did this. Actually, we can define means from this point is there, right? This point it is there, right? Suppose here one thickness you need, and here one like some 1 mm thickness you need, and here you need 0.5 thickness something you need. Like that it should vary 1 to 0.5 or 0.5 to 1, it should vary. That we call it as a gradient, so that pore size also get reduced. That we can define actually. Yeah, features are available, but the thing is, end top there is no feature like uniform lattice or gradient. We need to do that one actually by using the some other option is there. Till now whatever I have designed, that is uniform lattices. Uniform lattices means the thickness is uniform, pore size is uniform, every property is uniform. Gradient means from point to point it will change, right? The thickness and the property, so the property, stiffness, everything will change actually. That's why we call it as a gradient. That feature is there available in end top. That is called ramp. It is there. There we can do like. Wait, I just want to show something. As Sarah asked about that one, right? I will show. Yeah, this I have designed here. See, you can see bone uniform is there, and the gradient type A, type B. Something I have defined. Like suppose type A means here you can see in the geometry. See here you can see the thickness is uniform. You can see here the pore size and thickness is uniform. But here you can see the thickness is very less. Here once we go through here, the thickness is increasing, right? That we call it as a gradient. See how how much thickness is here and how much thickness is here, right? And this is like type B, and from center to till the end it is. Oh, is it? Okay. Now is it okay? Okay, okay. Thank you for that. Okay. So now you can see from center to here, this is changing. Like suppose if you want to explore about the more about the lattice and all those things, means you can go through here, and I mean my, since I have designed this, some of the application, yeah, I have given this. Yeah, like some of the one which I showed you in the animation video, right? Apps, I told you app, right? These things are there actually. We have designed, we can download it, and some of the structures which I took it in the NTOP only. This thing, texture I told you, right? This thing we can do, and medical applications, how we are using this lattice and all those things, that you can find it actually. That is how that gradient is possible actually. I showed you this one, right? This is actually gradient, type A, type B, and this is actually uniform. Uniform means same thickness is there. So this is how we can, like one example is that we took the we have designed the 3D lattice structure, like just to do the compression and all those things from the implicit body. And the other example is the tensile body. Since we can't able to draw the tensile body in the NTOP, so we have designed in the software, and we took it from the, I mean CAD software, we took it actually we imported into the NTOP, and we have applied the lattice here, and we can convert into, we can combine the three bodies so that convert into a single body and mesh it and import into STL file. Okay, export into STL file. Till now any doubt is there? Gradient we have completed, like how to, what is the meaning of the gradient? Any doubt? Nothing is there. Then we can proceed for the other example. Two example we have completed. One is like a cube lattice, and the other example is the tensile, and the next one we can go for the bone. Yeah, that is ASTM E8 standard. I mean the one which I used for to my study also. Particularly what you are asking, lattice structures or tensile testing lattice structures? Yeah, why I told you, right? Because that gauge length only, our attention is to go for the gauge length portion of the, right? Even though if you are design, that will go into the gripping portions. The left side and right side will get into the gripping portion. So how it is failing, we need to see in the gauge length portion, right? That also we can do. Okay, okay. Yeah, yeah, I will tell you. Like the failure are asking, like or the cup and cone. If it is like a cylindrical cup and cone, and if it is like a shear failure, something we can see like this, right? The thing is, the failure for the different structures, the failure is different. That's why in the video I have shown you, right, the geometry variation is different for different lattice structure. So the properties is also different actually. The properties and the failure is also different. And we did means one of my course scholar did on this thing, tensile. My work is on the compression, so I did on the compression and the application point of view. Whatever the slides I have shown you, right, topology optimization, generative design, that I did actually. So this also we can do, like the failure and this thing is there, right, that you cannot expect a shear failure or something. That may fail, some brittle failure also will happen. And if you go for the strut based lattice structure, okay. And if you go for the some other structures, means the failure, strut based lattice structure means the failure can occur in the, like the junction points is there, right? Why we are getting the junction point means because of the sharp corners is there. Stress concentration, we might have heard the name, right? Because of the sharp corner, stress will be concentrated there. So the failure can start from there only. Sharp corners. So to avoid the sharp corners, designers how they are thinking that designers how they are thinking means they have applied a fillets at the sharp corners. Long back previously they have used a strut base. Later they have modified into sharp corners because they are getting a failure at the sharp corner. So they have applied a fillets at the sharp corner. Still they are getting a failure. They are getting less properties. So they have opted the TPMS lattice structures. So to improve the properties, and we are not getting, there is no sharp corners in the TPMS curve because that is the curvature geometry is there, right? One point to one point it will change it actually. There is no standardization, sir. It depends on your requirement actually. You can increase, that is not an issue. Wait, I will tell you one example here. What is that? If you increase the unit cell, then support structure, like the force is there, right? The curvature is there, right? Anyway, we are getting a hole only, right? This much of hole we can print, but if you increase the hole size, for SLM I know because I am working on the SLM and I have referred the papers. There is like a masquerade one guy here, this is a masquerade. He worked on this actually. What is the bed size for the lattice structures to print? And he told that 5 mm is a good size to print because support structures. Later we can print without support structures, but the problem is that it will fail, deformation will occur. So because support structure 5 mm units are there, we can print for SLM I am saying. For FDM it can increase beyond the 5 mm also. Okay. And in our design we use actually 21 mm tube, is already there in the diagram. 21 mm tube lattice and 3 mm unit structure. That is the use. Because if you the problem is with this, like what I do the problem is, since we are using a metal structure and I cannot go test it with a 100 kilometer smoothly because that is going beyond the, that is taking your units of the, there is a, again it is going to be like testing media and doing testing media like this. If you take it with a 150. Just saying you have to. Now is it okay? Is okay? Okay. Yeah, where we are? Yeah, testing. So like I am using a the testing properties will depend, as already sir asked, right? Like if I am going with the 5 mm or something, the thinking what will change means porosity will change actually. Pore size is increasing means suppose in the okay, I will show you the weight saving something, the one which we are interested. How much weight is saving with this design? I will show you. Left, middle, right, see with this we are increasing at 10, almost 9% of weight saving means 91% of material is presented here. Suppose one more thing, one more design I will show you, that bone I will show you, there you will get the clear understanding of the porosity and all those things. 9% of material is there means 91% material there means 9% porous is there, okay. Here you can see the number. We'll do this. Yeah. Break, huh? Okay, we can go for break, then we can go for the remaining things, and the 3D expert also we can do. If any doubt is there, I will be here, you can ask. Any doubt you want this? లేదు ఇదే బెటర్, అదే ఇదే బెటర్లే. అక్కడ ఎవరు ఉన్నారా ఆపరేట్ చేసి, మళ్ళీ ఏదైనా ప్రాబ్లం అయితే అందుకే ఎవరో ఒకరు ఉండండి, ఫోన్ చేయొచ్చు. అక్కడ ఏదైనా ప్రాబ్లం అయితే ఎవరో ఒకరు ఉండాలి, మరి పరిగెడతారు సిస్టమ్ కనెక్ట్ అవ్వకపోయినా నేను చెప్పడానికి. నువ్వు వెళ్ళలేకపోతే నీకు తెలుసు కాబట్టి నీకు ఫోన్ చేస్తా, నేను చేసుకుంటా. Shall we start? Am I audible? It is there. You can get it. Okay, you might not know. Okay, there are some websites are there, like to download the 3D models, GrabCAD, Thingiverse. Some websites are there. It is there in my app also. Okay. Yeah, I downloaded from the Thingiverse. I think. Yeah, Thingiverse. 3D printed models you can get it. Bone, this I have downloaded, and I told you right, for bone and all those things, that is like a scanned models. We can get the tessellations. You can see there is no square type of thing here. That's why I zoomed it here. All are like a triangles only. You cannot find it square type here. Okay. THINGIVERS. Yeah. Yeah, sure. This one, bone. The models which I told you right, you can get it from my website, like this one. So the model which I told you right, like I can't say every model how I designed. I can't go beneath the layer, so tip of the iceberg I can give, but the 3D models you can download it. This is the one you can download it, okay? And Thingiverse, this is the one, bone, you can get it here. See, this is the one, bone, you can use any bone. There only I get it. And Thingiverse can download only STL files, remember that. There is no CAD model. GrabCAD means, as the name itself, you can get the any CAD models. Whoever the person, like the designer uploaded, suppose if I am the designer, I uploaded the step files, STL files, and if I design in the SolidWorks format, I can upload the SolidWorks format, like that. That's all that website can take it, okay? So this is the meshed body. So tessellation get confused. So like this it will come, right? So what my objective is to, I need to apply a lattice here. In between I need to apply the lattice. So previously the same thing here also there. Tensile body is there, right? Left, right, middle. Same thing. But this is the STL body. Previously we have designed the CAD body and we have separated in the CAD software itself. But here in NTOP, this is the STL body, and we cannot do the separation in the SolidWorks or CAD software. So we are using the NTOP here. How to do that means, first we will convert into, and I told you right, in NTOP we can play with the implicit body. Once we convert into implicit body, then only we can do whatever the operations, Boolean union or some cutting, subtraction, these things. So first we need to convert into implicit body. Okay. There is an option called implicit. See, this is a meshed body, right? So implicit body from mesh. Okay. So I will import this one, I will drag this one. You can see here, I told you right, icon, globe, network symbol, globe symbol is there, here also globe symbol is there. So this will accept, or otherwise double click on it, available options it will show, max underscore 1 name. Okay, you can get this one. See, it converted into implicit body. See, previously our body is like this, now our body is like this. Okay, so now we can do the whatever the operations we can do now. Okay, so first what I will do means I will separate into two bodies. Okay, like this is left, right, and middle portion like this. It is there actually, it is there like this, and I need to extract the middle body. So what I will do means I will take a planes and I will cut it. With respect to that plane I will cut it like this. I will take a plane, this is the bone is there, right, like this, some like bread is there and knife is there, we are slicing into like this. We are slicing means it will separate like this, right. Same thing means plane I am taking, plane your plane normal is there, I am taking like this. I will show you. So for what is I told you, right, entropy is like if you understand the Boolean union, subtract and interaction, then you can understand the entropy. So subtract we will see, then union we already seen, combining the three separate bodies. Three separate body means that should have a contact, then only the meaning of the union is had a purpose, right. If the body is one body is here and the other body is here, means there is no purpose of combining actually. Okay, that should have some contact. So once we convert into implicit body, then we can separate the body and we can extract the middle portion. How we can do means, so Boolean subtract, my primary body is this one only, in this only I need to do the operations, right. So that is my primary body. See, icons are there, I can drag it and I can place it here. Okay, remaining blend radius I am not exploring, you can get it in the help also. I will keep this as the same. So what I will do means I will subtract with the plane. So the subtraction body is the plane, this is the body is there, right, one body is there, and I am applying a subtraction here with respect to this plane. So this body can separate, how, from primary body. Okay, so I will take plane from normal is there. Okay, see, your plane is here and this is the implicit body and my plane is here. So I need to drag this plane. Okay, you can keep it. Okay, we will see how it cut it. See, like this we are getting, right, but I will perform in a one single stroke. I will extract the 3D body, I mean. Okay, we will see. So one more plane I will take it, this is the implicit body, right. See, this is removed and I need to remove from this side also, right. So one more plane we will take it, plane from normal, or otherwise I will copy the same plane, Control C, Control V, and this one I will see, this symbol is there, right, that is the toggle visibility. Okay, so this plane I will drag this here, so I will be here. Okay, now we will see how it can. Again we are getting this one, but we are getting the same direction of the plane. See, this plane is in the same direction, this plane is in the same direction, right. So I will change the direction, one direction I can change it. This I will keep -1, I will see. Oh, both the planes are same. Okay. Okay. okay, minus 1 plus 1. Yeah, see, I am getting the middle portion, right? See, previously this is the one, and I am applying my body here. I am applying, my intention is here only. So the remaining portions are the, this is the design space, remaining portions are the non-design space. I don't want to apply the lattice there. So I separated here. So you might have a doubt, we can do the same operation in the SolidWorks or other software also. But the problem is, SolidWorks means STL files, we cannot play the STL files, right? So NTOP or Magics, like Mimics, these things only STL file can support. There we can separate the bodies. But I am using the NTOP and I am separating the two bodies, okay? So I will apply the lattice. First what I will do means, this body is there, but the other two bodies I don't have, right? So initial body is there. Again I will take the subtraction from this, okay? You understand, right? Suppose this original body, from this original body, if I separate this body, I can get the remaining two portions, right? I will rename this one bone under bone lattice. Otherwise, design space, right? So again Boolean subtract. So my primary body is my original bone. I will take this name as a bone, original. Now just to identify easily, I am renaming this one. So original, if I type bone original, and the subtracted body is the bone design, okay? See, I am getting this one, right? So this is my non-design. Yeah, this is my non-design body, means my lattice won't touch there, okay? Non-design, okay? So I will apply the lattice to the bone design body, this one, okay? Again same thing. See, I already applied here, you can see here. Okay, I will apply once. Let's see. So my volume is that implicit body. Volume obviously implicit body I should apply. So what is the implicit body means? This one. The design body I need to apply. So I will drag it, double press on it so that you will get the available options. So I will use the wall TPMS unit cell. This time we can use the diamond. I will increase the unit cell size. Like 3 mm. Yeah. So I will further increase the unit cell size to get to see the pores. Okay. This each wall is there, right? That is of 3 mm thickness. Okay. So this one is there and this one is there. Now again same thing, same operation. We have completed this tensile operation only. Again once we are getting thing, we can combine the two bodies, right? So Boolean union. There is some one part is there, intersect is there. Intersect means common portion we will get it, okay? So two bodies we need to combine, okay? See, we have combined the two bodies. And if you want to extend this further, you can increase the plane. Plane, this is there, right? Here planes is there, right? Here one plane is there, here one plane is there, right? See, we are cutting like this, right? we are applying a plane like this, our plane perpendicular is there and we are moving like this, okay? You can increase the further so that you will get the bone lattice portion is there. I have randomly I put the length and all those things. Like this you will get the bone to the lattice body, okay? The same type of design is already available there, you can get it here. Gradient also it is there. So clear? Then if you are clear, then we can go for the engineering component, that is brake pedal. Any doubts is there? Yeah, forgot. Well, like weight saving? Yeah, I forgot. I will see. I will do. Yeah, see, weight saving is there, right? That is important finally, because so I will rename this as a bone with lattice. Now, why I am renaming this one means later like wait. I will show you one thing. See. Yeah, actually this project is there, lattice structure applications is there. There are like some hundreds of designs is there in the file, like it is of 2 GB file is there, hundreds of designs are there. Like if I didn't rename anything means implicit body 1 means it will go like implicit body till 1000 or something. So each one I have renamed the separate file, like some French's something is there, right? So French's body, French's original, French's lattice, like that I need to rename. If I didn't rename means it will go, you will get the confusion while applying the so many operations on these things. That's why I'm like it is a good practice to rename it actually, okay? So bone with lattice, that is a lightweighted body, right? Bone with lattice. Okay, and the original body is that bone original, I think. Yeah, bone original. Okay. Yeah. And topology actually use the topology optimization, but Fusion 360 will use the generative design. The thing is like right now I am learning that, so I can say this thing. It will use the cloud credits like in AI is there, right? AI, if you want to generate image means we need a prompt. We need to buy the prompts, right? For it is open secret. Like for educational one, if you are using for the educational purpose, you can give the Gmail also. You will get the unlimited credits actually to use the generate design. After 2019, I think they have adapted this one to give the education license unlimited credits. We can use the generative design for Fusion 360, and what I like as per my information, only Fusion 360 is the one who is using the generative design. Remaining all other software like ANSYS, Abacus and Entop are using the topology optimization only. Only Fusion 360 is using both generative as well as topology optimization. Generative design in Fusion 360, like I am using student version, so I don't know whether that module is there or not, but generative design is there in Fusion 360. It will remove the material, unnecessary material it will remove. Yeah. Yeah, like branches something like bow. Then that is not there in actually here. That you can go for the Entop one. I told you right, like MS lattice is there and Entopology is there. These are the two one, but in Entopology you can play with the surfaces and all those things. In that you can do it in Entopology. Like the simulation we can do. Like we can topology optimization will take the load simulation actually. Yeah, as well as generative design also will take The basic idea of generative and topology optimization is that we need to get the best result by taking the, it will take the objective, your objective is to get the good result by maximizing the strength and reduce the weight, and the constraint is that it should not exceed the this much of it should not remove this material, passive region, non-passive region, like the design space, non-design space, and it should not exceed this much of stress that we can, that these are the constraints actually. According to that, it will generate the design or it will optimize the body, that we call it topology optimization. Algorithms are different, both the things. There generally no actually. That we can do actually. Yeah, after topology optimization, we can incorporate the lattice. I mean, yeah, like I don't know how to say, like it is like related to my work only. Like that only I did actually. Like after incorporating the, after completing the topology optimization, like previously I showed you, right, weight reduction method. These are the some weight reduction methods is there, right? Based on that, I wrote a one paper. Like I took a one bracket is there, and I applied the topology optimization, and I applied the lattice structures, and I combined both topology optimization as well as the lattice structures also. These things I did, and you asked the gradient, right? There also I did actually both uniform as well as the gradient lattice structures I applied. Like I just want to explore the how much is the potentiality of these methods are there, and how much weight reduce using these methods. Yeah, 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 yeah. That, yeah, that is the problem. And the simulation part you can do the NTOP, but the problem is that we cannot trust the NTOP results, so we are using the abacus explicit analysis. There we did, and I used abacus implicit analysis, static analysis I did actually, not dynamic. Dynamic also, dynamic you can see the real time data, these things we can see. Abacus is good to go for the NTOP parts to do the simulation. No, but we can apply the, like lattice to the topology optimized body, but generative plus lattice structure, it is not there actually, it is not there, I understand. And the thing is, only Fusion 360 have the ability to do the generative designs, because it will work on the AI based designs, so it will take the cloud credits and all those things. And education license, it is unlimited, you can explore it if you are applying the education license. And remaining other software is the topology optimization only, as per my information. So that is how you can design the 3D model, and if you are extending this operation, you can go with the, you can increase the lattice length and all those things. And the density you can see 13 point, like weight saving is 14%. And if you want to increase the weight saving, what to do? If you want to increase the weight saving, what to do? Suppose, okay, this is the basic actually. How to increase more porosity? Reduce the thickness. If I reduce the thickness, then the component will be lighter, right? So porosity, pores will be more, right? Or otherwise, increase the lattice size, like some 50 mm cube is there. I am applying 5 by 5 by 5 means how many things I am getting? 10 into 10 into 1000. Suppose if I am applying 10 into 10 into means 5, 5, 5, 225 will get it. 225 unit cells I will get it, right? So unit cell size get reduced, so the lattice density will get reduced, right? That is how. I mean, these are the parameters you can do the optimization, like how to increase the porosity and all those things. If someone asks means increase the unit cell size, means decrease the number of unit cell size, okay? And the decrease the thickness also, there, that also we can do, okay? So that is how we can do the bone. And there is one more option is there, engineering brake pedal is there. Okay, we will export it. Okay. Yeah. See again, this also like I told you, right, design space and non-design space is there, right? This is the best example. You can see it here. I will tell you, some holes are there here, but I cannot able to define the design space and I cannot able to cut it actually. That we can do it in NTOP easily. We will see. And I already separated this body. My intention is to apply the lattice here. So I separated this body in the SolidWorks only. See, in this body I don't want to apply the outer body lattice, right? So I want to apply the boundary region. This boundary I have confined, so I will apply the boundary. I have defined the boundary, I will apply the lattice here, okay? So first what I will do means, we will take this into new section. Close this, okay? First I will convert this into the implicit body, okay? I will rename this one break. This is your design space, okay? And this is, and how to convert into implicit body means, press one time you will get the face. Press again double click on it, you will get the, you will select the entire body, okay? So one time I am selecting the face, right? I am pressing two times, I am getting the entire, I can able to select the entire body. Right click on it, convert, create body into implicit body. This is break, non-design space, okay? Okay, now I will apply the lattice. This is the one I will drag it. Acha, you tell me which lattice I should apply, whether I should apply the graph strut based or 2D lattice or TPMS lattice. In TPMS I will ask you the which one I should apply, and you want to see gyroid, okay, that is TPMS then. So wall TPMS, gyroid squash is there, so this I will increase the thickness, otherwise processing time will increase. 15 I will keep, later we can see. And thickness some 2 mm we can see. Oh sorry, non-design I kept, okay, design I need to keep, okay. So we can increase the thickness. See this is how we can get it. But here the problem is that my attention is to complete the body. I can able to get the design, and I can combine this one non-design. Finally I will get this one. But here one problem is there. Can you able to see? Can you able to say? See here. Okay, this is a good thing, and here surface is there. See, suppose if I am applying a bolt, means will it able to fit? There is no threads, right? So that we need to define it as a non-design space. How to define means, this we will see the Boolean intersect. Here only it will come actually. So again we will go for the imported body. This one is there, right? This I will select it. These two bodies I will select, whole faces I mean. Those two faces I am selecting, and what I am able to see means I will convert into implicit body. First I told you, right, whatever you want to do the NTOP operation, we need to convert into implicit bodies, okay. First I will convert into implicit bodies, and I will thicken the bodies, so that you will see that. Control, select the bodies, okay. Convert CAD faces to implicit bodies, okay. See, total 3 bodies are there. See these 3 bodies, okay. So I can apply the thickness to the faces. This is the surface, right? So I will apply the thickness to the surface, okay. Thicken body. So I will drag this. See, the symbol is same, right? I will drag this. I can apply the thickness 5 mm, okay. This is okay. Wait, we will see now. Design, right? Is this okay? Are we getting like this? See, this is the original design. This is the one we are getting, but the whole is not in proper, right? So here is the one we need to apply the intersect. Intersect means common body, it will remove it. It will find the common body, right? So that we can find it, okay? So Boolean intersect. And see, the thing is, this is not even moving. Why it is not even moving means, this is like a two separate bodies, right? So the best way to say this example means, I am deleting this one. Why I will say it? See, I will delete this one. I will take this as a single body, and I will do the Boolean union there. Sorry. See, here you can see three bodies are there here. 1, 2, 3. Three faces, three bodies are there. Thicken. Okay. Three bodies are there, but three bodies are not in the same bag. Okay. We need to keep those in the same bag. Then only we can take it into some other place, right? So how to do this means, first I will take the Boolean union. I will delete this one, because this is as a single body. There is no primary body and secondary bodies. This is as a single body. Those three are separated. We need to take that in the single bag, right? So I will take this and delete it. I will drag this one, so that now this will be in the single body, okay? I mean the shape didn't even change. Now that can take it as a single body. Okay? Like this. Now we can export this one. So this one, and the other one is this one. This one and this one, right? Or otherwise this one we can take it. Okay? This is what is the name of this one? I think design or non-design. Yeah, design means the one we are applying. We are able to tweaking of the design. Okay? So brake pedal, brake design, I think. Okay? See, we are getting right. Now we will see. So is this okay? We can print it, and we can do the threading operation. We can apply the bolt, right? And you can see this is there, right? Why we are getting this bolt head is there, right? It depends the thickness. You can change it actually. If you increase the thickness, the bolt head, it depends on the bolt head thickness also. Like that you can change it. That is bone. No. This is actually that spline curves is there, right? Initially it is there like this. See, this curve is there. According to this line, I did actually. This type of operation we can do. Actually, that is like a different part. Like SolidWorks, we can do. There we can separate the body using the curved path actually. Splines or other, we can separate the two bodies. That is a, I think, no, step file is there, okay. Actually I did in the I designed in SolidWorks, and I separated this body in the SolidWorks only. There I did actually. So you will get it there, and you can separate it. Bone means STL, right? So we cannot play STL in the SolidWorks. So that's why I prefer the NTOP here. Okay. We can combine these these bodies. Which are the bodies? This one. Why we are applying this one? We are getting the non-design and this one. So we can break underscore non-design 2. Okay. So we can combine these three bodies now. Boolean union. How many bodies are there? So here 2 is there. You can click on the plus, you can import it, okay? This one, and non-design. Okay. Oh, both non-design applied. Okay. Non-design 2. this one, here this one, yeah this one, sorry. Okay, now we are getting the final design, right? Our holes are, we can preserve the holes and all those things. The main thing is how to identify the design and non, I mean whatever the terminology is same for the both generative and lattice as well as the topology optimization also. The main thing is the preserved region and non-preserved region. Non-preserved means design space and non-design space. These are the non-design space. Always think about it. Holes are the non-design space because that hole has some purpose. We need to put a bolt on it, and we need to do a threading operation. So that should be in the solid format only. That's why we kept it like that. Okay. So that's all from the NTOP. If you have any doubt, you can ask. Otherwise, we can go for the 3D expert is there, that we can go it. Any doubt is there? What's that? Foam. It is there actually. Yeah, it is there. Stochastic means Varna, it is there actually. Varna structure we call it as a. It is there actually, I will show. I mean, I didn't explore all these, I forgot to tell all these options actually. Simulation you can do here, I told you right, the simulation structural and these things, static, model, buckling, thermal we can do. Yeah, stochastic you can see here. Their Warner surface is there. On the surface also we can, like whenever the texture we are saying means that will be applied to the surface only. The term we are using texture means that will be applied to the surface bodies only. That is not applied to the 3D body. Okay. Surface lattice means we can apply the texture. Volume lattice means entire body we can apply. Warner we call it as. It is there actually. Warner means random points it will apply there. There is no uniformity actually. That we call it as a Warner. Is this okay? I mean, this is not, I put a lattice actually. You cannot able to get the unit cell. I told you right. Warna means that should be in the random position. From one point to one point it will change actually. So if I want to reduce the size means, like this. See, there is no uniformity in this actually. And one more thing is like, I mean it is going beyond, like see here you can see this one, right? The tapered portions is there, right? But that we should not able to get like this. You can see here the tapered portion. We need to get exactly means we can go with the Boolean intersect here. I will show you. Oh, it is hanging. So can I show this later, like it is system is hanging, because 3D expert is also there, that I will show. Anyway, some people are there, they are interested to know about Dentop. I will take to the lab and I will show. I will use the same body, so I will combine it. You can save this. Combine. Okay. So is this visible, right? One more print. Okay. Okay. అదే కావాలి. So we can add the component, and the thing is, this is the 3D expert is the slicing software for the 3D systems machines. 3D we have, since we have a DMP Plex 100 which is supplied by the 3D, you can see the name DMP Plex 100, which is supplied by the 3D system. So they have given the software 3D expert to generate the tool path to put it in the machine, so that we can slice the 3D model. That we can see it now. So we can, same thing, import the component, like in Dentop also same thing. In every slicing software, what are the conditions we are doing means, first we will import the slice, we import it and position the body, and we can generate we can apply the lattice structure, whether any war, like you know about it, right? When can we apply the lattice structure, whether there is any horizontal bridges or overhangs is there. Since lattice is AM is a layer by layer process, we need a lattice what we call support structures, right? So there we need a support structures. So first we need to add the 3D printing component, position it and apply the support structures, and we can give the parameters and we can generate it. We can send it to the machine. Okay, send a G code. Okay, first add a 3D component. I will add this. So I will keep the same position. See here. And has already sir told yesterday about there is a some like this is not for all, like as my knowledge I will say, like because you might industry also, like as per my knowledge, for roller support, roller, like this is roller based AM machine. So what will happen, I will tell you. See, suppose this is the thing is there, right? I mean I cannot go there. That is like a straight path, right? Suppose this is the roller is there, and my body is like this. Yeah. My body is like this, and this is the roller, right? Suppose I am applying this one like this, there is a more contact is there. Suppose if I am rotating this one, your roller is there. There is very less contact. I am moving here, less contact. The very starting position, that should be in the less contact actually. Suppose if it is like this, your entire surface is in contact. Like during the very roller is moving like this is the first wave or bill plate. The first part touching is very high contact area is there. So the bill get failure. So what they suggested means they will ask you to rotate the body into 5 or 10 degrees so that the contact can reduce. That is the recommended actually. So we can position the body first. I will apply the support structures here so that you will get to know. Okay. So one I will keep. Delta Z means height actually, like this. Okay. And Z axis I am rotating some 5 degrees. You can change it here 5. Okay. I will be okay with this position. Okay. But there is a problem with it. This is an overhang position. I will show you. And why I am applying some particular height to this? Why I need to apply the support? I can print it directly, right? This, that is why. Suppose here I kept it, I have designed with a 10 mm, but your tensile usually ASTM 8 standard tensile sample will be 2.5 to 3 mm thickness is there. Suppose you have designed with 3 mm, you need exactly powder limitation is there. You need exactly 3 mm output or 2.5 to 3 mm output is there. So for that what we are doing means we are adding a support in between. And if you are adding a support means the SLM, like the support structure means the parameters are different and the like heat accumulation is there, right? That will be more, and we can get a good print if we are applying a support, be it a solid body or be it anything. We can apply the support some, but here I kept a one body 1 mm. It is recommended value is 0.3 mm to go for the wire cut TDM. 0.3 mm is enough. Just to apply some different supports I just kept. So support manager I will keep. See, these are the parameters. 30 is there, I can keep it as a 45. Anyway, here no overhang angle is there. So I will keep OK. And this will automatically select the area, you can see here. See, this is automatically select the yellow colored area, right? This will automatically select it actually. So again support manager, see that is the reason we are getting here. See, we are getting the reason, right? So I can apply the support. If I am going with the wire cut EDM means I can apply for the solid support so that I can remove it. But to reduce the post processing time means wire cut EDM, and to reduce the material means I can apply some other material also, like wall type supports and all those things. First I will apply the solid, later we can see the other support. So I can go with the skirt support, that is also solid only. Like in between bases we can apply the skirt support. So I will select this. Solid support. Yeah, skirt here it is there. Okay. Yeah. Since the height is 1, we can tweak this value. I will keep this as 1 since the height is 1, so that we can get the chamfered shape. See, we are getting this chamfered shape, right? Otherwise you can keep with the 2 also, no problem. Like this. We keep this 1. Okay. So this is the one, body support, you can see here, support body. Okay. So for the single body we can apply the slicing to reduce the time. So first we can go for the calculate slices, later we can define our own parameters. First we can slice with the default parameter, later we can define our own parameters. So first we'll go with the default parameters, click OK, and we are applying a 17.4 pH. You can change the material also, titanium and aluminum, cobalt, chromium, whatever the machine can support. So it will scan the path, and once we are completed this calculated slices, then we can change our parameters as a scan path manager. You can see here, scan path manager is there, means we can manage the scan path. So recalculate slices, and again our intention is to apply the anyway you don't need to work out on the parametric optimization on the supports, right? Because we are removing the support. Our main intention is part, right? So our parametric optimization is on the part. So two types is the part as well as solid support. So our intention is to go for the part. You can see here, settings, General parameters means layer thickness we can see here, layer thickness 30 mm we are keeping. You can calculate the number of slices, 367 I am getting. And hatching parameters, main thing will come here. Hatching parameters means scanning related parameters like scan speed means laser parameters. Hatching related means hash distance and the scan pattern, these things we can change it. Okay, you can see here, this is like a hexagonal, you can see the thumbnail here, rectangular, and if you want to go for the alternative means chessboard actually. Okay, vertical, these things are vertical, horizontal something is there, strips is there. I mean here how many scanning strategies are there means strips we can do, rectangular we can do, and rectangular alternative means chessboard we can do, island scan strategy we can do, hexagonal we can do. Okay, again strips horizontal vertical both these things, double centering we can do. And the side step means distance between the hatch spacing, you can see these are the lines is there, right? Each hatch is there, that will go very fast actually in the during the like printing, you can see the how it is printing. So that is the distance between hatching. Suppose if you want to change this 50 to 45 means we can change it. And strips to, by default it is hexagonal, so I can keep it as a rectangular, alternated means chessboard it is. Yeah, laser parameters you can change it here. Part right, yeah, part. 100 watts it is there, you can keep it as a 90 watts also. And 1200 mm layer, these are the default parameters we are using for here. And if you want to keep 600 or 1000, you can do that also here. So if I reduce the scan speed, what will happen? I mean apart from the defects and all those things. More time to scan, right? Right. I mean defects you can forget, like after printing only we can see the defects, but printing time we can see in the software itself, right? That is what. It will take more time. But sometimes we need to compromise on the scan speed also, because optimization is there, right? That we need to compromise also. We need to go for the less speed also to get the better relative dense components. Okay. Defocusing also we can change it, but usually we usually keep that only. We can change it also. That, yeah, variable parameters we cannot keep it here actually. The thing is, the one more thing you can do means you can arrange the like a what we cards pattern. Cards are there, right? Card house is there, right? Arrange it. You can arrange the two different bodies and you can give the parameters for different. Segments means what is the what if that is not there here actually. Even though it is there, we didn't explore it much. Maybe in the advanced version it is there. We are using the basic version of 3D Expert. Some parameters we didn't even touch also, because our main intention is to print it, and to get the printed means parametric optimization, that should be in the dense component. So that we have completed successfully, and once we get the parameters means we are going for the application point of, like I showed you, right? The brake pedal and hip implant is there, right? Those things we are interested to print it, and we have printed also those things. And the lattice structure, these things we are using. That is what. Actually, the problem with the lattice structure specifically for the PBF I am saying, not a SLM, not a powder based technologies. The powder get trapped actually. While using the whatever the lattice you printed, the powder get trapped inside. If you see any paper or research paper or something related to lattice structure, PBF technologies, there must be say unmelted powder. Yeah, partially melted or unmelted, uncentered particles, whatever it is. Uncentered particles are get trapped inside it because the, yeah. Yeah, we get a difficult in start base because the that thing what will happen means during that time this is like a three junctions are there, right? Three junctions are connecting here so that the multiple formation will be higher here, so that the roller axis error we are getting there actually. So we stopped the start basis. Anyway, our intention is the TPMS because TPMS has a better properties than the strut base. This we have scientifically proved in the have we have printed in the FDM lattice. FDM printed we have tested and we have scientifically proved it actually. Yeah, octet, yeah. T- like so I will tell you the example. Suppose if you are taking the same porosity like octet and gyroid or some other TPMS structure with the same porosity, 50% porosity, 50% porosity, I definitely say that, yeah, this is one of my paper also there, like I compared these two. In some properties octet is better, like the same thing actually, octet and gyroid I did. In some properties, and that property is that Young's modulus is there, stiffness is there, right? Octet is better because that is like a stretching dominated. Always remember, like I mean this is like a lattice testing parameters like terminology. Stretching dominated has a better stiffness properties actually compared to bending dominated lattice structures. Yeah, all the TPMS, most of the TPMS are the bending dominated, and for strut based, how we are saying stretching and bending dominated means it is it depends on the Maxwell's number actually. There is some formula is there for to calculate the Maxwell. Yeah, multiple. So we octet means we have printed very less sizes actually. Mainly BCC we are getting this problem. That time we kept 1 mm I think. Yeah, 1 mm or 1 mm. Hmm? Radius, or we call it a thickness. Dia. No, 1 mm dia, 1 mm dia. Sorry, okay, you are saying, okay, 1 mm dia. Yeah, yeah. And we use it to print for the SLM sample, we are not going beyond like 30 mm cube or something, 18 mm or 21 mm or sometimes 15 mm also. But for FDM, we use it to print 50 mm size lattices actually. Because FDM is yeah, we can easily do whatever the things we want. That is what FDM. Yeah. Yeah, why? How we are saying optimization means there should be some parameter output is there, right? Based on the output, we are saying this is a good parameter, right? And there are in journals I am saying, I mean, whatever the my knowledge, whatever the my like research, like I found that the researchers focusing on the two output parameters. Some people are working on the relative density or porosity, good dense structure they are applying, or otherwise residual stresses is there. If the same parameter is giving the best dense results, but very higher residual stresses means they will leave the parameter. Both the thing they are calculating. The same parameter is giving acceptable residual stress means they will go for the higher dense structures. The same parameter they will use for the mechanical properties actually. That is how I did also my research. And no. Yeah, okay. That geometry what we are doing means some cube samples is there, right? While doing the optimization, not only we, like everyone will print the cube samples, cubical samples, 5 by 5 by or 10 by 10 by 5 something, 5 mm height only or 2 mm height something. They will print it and they will test the relative density using Archimedes principle, and they will do the microstructure and everything. Using the relative density Archimedes principle, they will find the porosity, external porosity. No, no, no. That you are saying that related to design actually. That solid lattice, solid porous. That in terms of design you are comparing. But in terms of printer point of view, I am saying. But first we need to fix the printer optimization parameters, right? That only we are doing. Printer optimize. Once we optimize the parameters, then we can go for the design parameters actually. No, no, no. You are getting confused. Okay. Even wrappage is also there. Yeah. Hmm. Yeah. Because we are going, I told you right, our aim is to focus on the design actually. Design means we have printed the, like we means one of my course scholar is there. He has printed so many lattice structure using the default parameters only. In my case, anyway, it is completed. Like in my case, I did the process parametric optimization using the solid bodies, residual stresses I calculated, and solid mechanical properties I calculated. Later, once everything I got finalized, later I go with the lattices actually. Lattices, and I printed the applications using the lattices actually. That is how I did actually. I carry out actually. But one of my co-scholar is there. He is not worrying about the lattice parameter. He just did the parametric optimization and got one parameter, and he is playing with the design things, like different structures he is applying and he is testing, and whichever they getting the best results means Young's modulus as well as the, I mean, you may, if anyone know the lattice structure testing terminology, there is one term is called plateau stress is there. Plateau stress energy absorption is there. Energy absorption means toughness. In solid body toughness, there energy absorption. Mainly they are using shoe soles is there, right? There they are using lattice structure. Energy absorption, helmets is there. Car crashing test is there, right? There we can use the lattice structures. It already Adidas, I think, yeah, Adidas is there. Already they have printed this lattice structure for aesthetic purpose. They did actually. Some shoe soles is there, right? That they have printed. Oh, that okay. Actually, that video got famous. Like, even one guy is there. The tech guy is there. He promoted that video like airtight ball. It is actually airtight ball. Volleyball. It is there. I think so, right? They have printed using the SLS. Yeah, airtight ball. They call it as a airtight ball, named as a airtight. Wait. I'll show. Oh, I will show that. Yeah, this is the one I think. The volleyball with airtight ball we call it as actually. Sports we can use it. Airtight ball, like the same thing they have printed actually. I mean, I got inspired from that only, so I designed this one. Just to see volleyball as well as airtight ball. So, okay, we can go for here. So once we fix the parameters, we can say okay, save and close. Okay, okay, again okay. I think for body we have changed the parameter to rectangular, alternated, okay. This we can see in the slice viewer. Yeah. See, this is here hexagonal is there, right? You can see hexagonal shapes is there. Now again rectangular. Now part got started, right? Rectangular this is. And you can see here alternated lines are there. Here, like you have seen the chessboard, right? In chessboard, what will happen? Like the what we call, whatever the black is there, the surrounding will be always a white, right? Same thing here also there. This line is like this, right? The surrounding line won't be like this. See, perpendicular to this. This one surrounding, black and white chessboard. That's why we call it as a chessboard. It is black and white. Okay, like this. Always perpendicular. That like a hatching pattern will be the perpendicular one. So once we are okay with it, we can send this to print. Anyway, we don't print a single part. We can go with the multiple part. This same type of component is there for your printing also. That time also we can say this thing. We can show you in the build view. Fab3 file, the machine will accept the Fab3 files. So that is the one. Sorry that actually I focused more on the NTOP, so I cannot able to convey more information on this actually. But I will show one more thing, that I applied the solid lattice, right? I will show the wall type of supports, how can we apply. That I will show. I will delete this. Delete support, not region. So wall support. See. But the problem here is internally it is not applying. Wall means outer body only, right? So we need to do some other thing, that I will show you. Add pattern, so that it will add the pattern. Like this it will add the pattern, right? See. And square grid or something we can say, take it. And distance I will keep 2, so that we can get the more. Square shell. Usually prefer cross line or square grid. Okay, this one. Fragmentation means if you apply the fragmentation, there is some gaps is there, see, so that we can easily break it. Okay, the support, we can reduce the post processing time. This is one of the technique, fragmentation. Okay, so we can apply this pattern. Now we can go with the wall support. See, now this is this we are getting, right? But I don't want this to be a single thin wall, so I can keep this as a create solid wall. Okay, but internally this is the thin wall. Okay, outer body it will create the solid wall. Okay, now these type of supports we can easily break with the pilers also. Pilers are some post processing tail. There is no use of wire cut EDM here. Okay, we can use pilers and we can remove it. Again, once whatever if you change the position also, you need to do the slicing again. Okay, so we have already changed we didn't change the position, but we have changed the support type, right? So again we need to do the calculate slices. Again the same thing, the same story will happen. We calculate slices and scanning parameters, again slicing viewer, these things we can happen. But usually we cannot go for the one sample print. We can fill the build actually. Since we have a less memory of the laptop, so I use it to go like this. But there we can see actually. Any doubts till now, like in NTOP or anywhere? And in this also we can do the lattice also. But this is, I prefer the NTOP only. This we cannot able to control actually. They have given just to whoever don't have the NTOP license, right? There may be some useful for them. For that only they have given. But there is no control option here. So I prefer that NTOP is the better one for lattice generation instead of this. During at the base or at the base we have printed some solid wall actually. That is some trick is there, like we found it actually. Extra solid wall we have printed actually. Or otherwise we can create a solid wall like I told you, right? Tensile sample is there. Some 30 mm cube I want to print a lattice. 1 mm thickness I will add some extra base is there, that I can separate the body. During that time my design space is on the 30 mm and that 1 mm space is the non-design space. I will apply the 30 mm lattice here, non-design space I will combine it, I will print it. So the 31 mm will come. In that 1 mm I can cut it. Right? if you want a, like a polishing thing, you can use that, like a polished one. Like the wire cut itself is a good one actually. In the band for band side is not good, but wire cut we can get it. Correct. No, 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 it won't get damage. We already tried because that structure is the continuous, right? There is no discontinuity in the structure, right? There is a porous is there, but the wire will pass through the porous only. There is a porous is there, but the structure is the continuous. Like one point is there, it will move like this. I will show you. That TPMS you can see here. The structure is the continuous one, right? I mean, this will connect to other body. Don't get confused. This is a two separate body, mean that will connect to other body actually, the side body. Okay. And you can see, I told you right, the strut formation, we have printed the BCC, the problem with the multiple formation, here only BCC you can see. The 4 junction points the 4 points we are seeing, right, the 4 points is come in contact with each other. So the, specifically they told that for roller based thing be like this, if anything happen, that will be a problem actually. So the because of the 4 junction points, we are getting a difficulty. In octet, we didn't feel like this actually. You can see there, yeah, octet. Because octet is a different thing actually. So because of that only, we are getting a problem. So so the later we go for the TPMS structures, gyroid, split P, diamond, squares also we can do. These things. That thing you can see. That is TPMS and hexagonal square reentrant of the 2D lattice. Once I play the video, see the hexagonal is not changing because the other direction parameters is same, right? Okay. And the square simple game how it is changing you can see. Okay. That's how we can do. Any questions? Lattice, frankly speaking, since we don't have, like I can't say this, like since we don't have a measurement to calculate the roughness actually, the device we don't have, so we didn't, but the thing is, it is a very rough surface. Using the post processing we have improved the surface, that we can say, because we have seen because of the powder intact with the lattice, right, we are getting a higher, like rough surface is there. And sandblasting we applied actually. Once we apply the sandblasting, we are getting a, like I did the like morphology images, there I found it actually. There I said this actually. Using the sandblasting, you can, that powder intact with the this one, right, that we can remove it actually. Sandblasting thing. That is there. Anyway, tomorrow, I think day after tomorrow, you will get to see what is and how it will improve the surface roughness, these things, sandblasting. Post processing, we can see that. Anything is there? Any questions on N-top or this one? Anyway, N-top I took more time because, okay. No questions? Thank you. Yeah, we'll meet tomorrow at 9:30 a.m. with C. Channabhat sir. Okay.